How long do you think it would actually take you personally to get to Pluto if you used real engines we have now and real trajectories, not sci-fi shortcuts? Before you can answer that, you have to face a simple, uncomfortable fact. Pluto is not sitting at one fixed distance from Earth, and that single detail wrecks any neat, clean answer you might want. Start with the basic number problem. When people say, "How long to Pluto?" they usually picture one huge distance, like a wall you just have to cross once. In reality, Pluto lives somewhere between about 2.7 and 4.7 billion miles from Earth, depending on where both worlds are in their orbits around the Sun. At its closest, Earth-Pluto distance is still on the order of 2.7 billion miles. At its farthest, it stretches to around 4.7 billion miles. That means even if you keep the same rocket, the same fuel, the same everything, just changing the departure date can almost double or cut in half your travel time. The solar system doesn't care about your schedule, it only cares about geometry. So here is the first big question. Can you really talk about how long without first locking in how far on that specific day? Mission designers do not. They start by calculating the positions of Earth and Pluto years in advance, running through thousands of possible launch dates and asking, on which dates is the path shortest and most efficient? You're not choosing a road trip. You're picking a moving distance that keeps changing as both planets orbit. Now go one step deeper and look at Pluto's own path around the Sun. It does not move on a neat flat circle. Its orbit is stretched out and tilted compared to Earth's. Its distance from the Sun ranges from roughly 2.8 to about 4.6 billion miles. That means sometimes Pluto is a little less far out. Sometimes it is much deeper into the outer darkness. So even if you just talk about how far from the Sun instead of how far from Earth, you still get a range, not a single value. For you, that translates into this: every mission profile to Pluto is different. Some intercept Pluto when it is nearer in, some when it is farther out, and the time you spend in deep space can swing by years because of that. So the next question becomes, if the distance is constantly changing, can you at least use the fastest possible thing as a reference and see how bad it really is? That fastest thing is light. Light travels at about 670 million miles per hour. At Pluto's average distance from the Sun, around 3.7 billion miles, light still takes roughly 5.5 hours to get there from the Sun. That is not a simulation, that is just dividing distance by speed, and it should hit you hard if even light, which crosses the distance from Earth to the Moon in just over a second, needs most of a day to reach Pluto, your rocket, which is tens of thousands of times slower, is signing up for a very long trip. Once you see that, the obvious follow-up is, what happens when you plug in speeds you actually know, like a car, a plane, or an orbital spacecraft? Take a nice middle distance, say around 3 billion miles for a particular Earth-Pluto alignment. At 60 miles per hour, normal highway speed, you take the 3 billion miles, divide by 60, and you get tens of millions of hours. Turn that into years, and you are roughly at 7,000 years of non-stop motion. No brakes, no refueling, no tyre changes, 60 miles per hour, 7,000 years. Human history does not even feel long compared to that. Push the speed up to something that feels serious, a commercial jet around 500 miles per hour, same 3 billion miles now divided by 500. That still gives you millions of hours. Convert that into years and you fall into the 800 to 900 year range. In simple terms, if an airliner had left for Pluto around the time early European explorers were crossing the Atlantic, it would still be on the way. That sounds ridiculous, so bring in real spaceflight. The International Space Station orbits Earth at about 17,500 miles per hour. At that speed, it can circle Earth in about an hour and a half. Take that same 3 billion mile distance and divide by 17,500. You end up with on the order of 170,000 hours, which is roughly 20 years. That is finely human scale, but it is still brutal. A person could be born, grow up, finish college, start a career, and that station speed ship would still be coasting toward Pluto. Now compare that with the kind of speeds New Horizons actually use near Pluto, around 30,000 miles per hour and higher. Even if you pretended you could hold that high speed from day one over a roughly 3 billion mile path, you are still talking about around 11 or 12 years of flight time, and that is with an extremely aggressive, optimized robotic mission. The takeaway is simple. The distances are so extreme that even large boosts in speed do not collapse the time the way your intuition expects. Doubling your speed does not turn decades into months, it just shaves a bit off the decade count. At this point, it is natural to ask, why can't you just draw a straight line from Earth to Pluto and blast along it as fast as you can? That sounds like the obvious shortcut. The problem is, you're already moving. Right now, Earth is orbiting the Sun at roughly 67,000 miles per hour. Pluto's orbiting too, on that stretched and tilted path. The Sun's gravity is pulling on every object the whole time. In that environment, a simple straight line between two moving points does not stay straight or accurate for long. Here is the key concept you have to accept. You do not fly to where Pluto is. You fly to where Pluto will be when you finally get there, years later. Your path curves around the Sun. Pluto's path curves around the Sun, and you have to time your departure so that both curves cross the same spot in space on the same date. That is orbital mechanics in plain language. You're constantly falling around the Sun, while Pluto is also falling around the Sun, and your goal is to line up those falls. This leads to a kind of paradox. Going straight is actually the lie. The fastest, cleanest path in terms of fuel and physics is almost always a carefully shaped curve, designed so that the Sun's gravity and your initial push from the rocket work together. If you tried to ignore that and just point at Pluto's current position and burn hard, you would miss it by millions of miles, because by the time you arrive, Pluto will have moved far along its orbit. Every real mission solves this with careful trajectory planning, not with a straight line shortcut. So before you even talk about real spacecraft that have gone to Pluto, you already have the core answer to the first part of the question. You are chasing something that sits anywhere between about 2.7 and 4.7 billion miles away, moving on a stretched, tilted orbit, while you yourself are also moving fast around the Sun. Even light needs hours to cross that gap. Your car needs thousands of years. Your jet needs centuries. Your space station's speed needs decades. And any straight line you think you see is just a trick of your earthbound intuition, not how space actually works. The natural next question is this: has anyone ever beaten this problem in real life, with real hardware, and actually reached Pluto? And how long did that take when everything went right? You want a real answer to how long would it take to go to Pluto, not just back-of-the-envelope car and airplane comparisons. So here is the hard anchor point, the one time humanity actually did it. NASA has flown exactly one spacecraft from Earth to Pluto, New Horizons. It launched in January 2006 and flew past Pluto in July 2015. That is about 9.5 years launched a flyby. No guesswork, no theory, just a clean historical number. When you ask this question, this mission is the benchmark you are secretly asking about, because it is the only real case we have. Now here's the part that should make you pause. That 9.5-year trip was not normal speed. New Horizons did not stroll out of Earth orbit, it left like a bullet. At launch, it was moving at roughly 36,000 miles per hour relative to Earth. That was the fastest launch speed of any spacecraft at the time. In simple terms, that is about 10 miles every second. If a car somehow did that on a straight road across the United States, coast to coast, it would be done in under 5 minutes. So when people say, we'll just build a fast rocket and get there quicker, this is what fast already looks like in reality. So here's the question that should hit you next. If 36,000 miles per hour still leads to almost a decade of travel time, what does that say about the size of the problem? That was not a gentle departure. That was an empty the tank and throw the probe as hard as you can kind of launch. And even that was not enough by itself. About a year after launch, New Horizons reached Jupiter. This is where the smart trick came in. The spacecraft flew close behind the giant planet and used a gravity assist. The basic idea is simple. The probe falls into Jupiter's gravity well, swings around behind it and climbs back out. In Jupiter's own frame, Its speed barely changes, but from the Sun's frame, because Jupiter itself is moving around the Sun, the spacecraft basically steals a bit of Jupiter's orbital energy. The result: New Horizons left Jupiter going about 9,000 miles per hour faster than before, without burning a huge extra load of propellant. This one manoeuvre cut roughly 3 years off the travel time. Without that Jupiter sling, you're looking at something closer to a 12-year trip to Pluto for the same spacecraft and the same main engine. So now you have another key point. The 9.5-year number is already the cheated version, using a massive planet as a free speed booster. If you tried to do it purely on your own engines, with the same tech, you would slide into the low double digits in years. That creates a good tension, because now the question becomes, if you're already using the fastest launch you can manage plus a giant planet as a free accelerator, how fast are you actually going by the time you reach Pluto? And is that enough of it to make the trip feel short? When New Horizons flew past Pluto in July 2015, it passed only about 7,800 miles above Pluto's surface. At that moment, its speed relative to Pluto was still around 30,800 miles per hour. That is about 8.5 miles every second. Think about that clearly. 30,800 miles per hour. And it still needed more than 9 years of travel to cover the distance from Earth to Pluto's orbit. That is the scale you are dealing with. Even at that speed, Pluto does not feel close. The probe did not slow down to enter orbit. It just tore through the system, grabbed as much data as it could during those few hours near closest approach, and then kept going out into the Kuiper belt. This leads straight into the next uncomfortable thought. What would this mission look like if a crew had been on board, riding that exact trajectory? Take the same departure, the same Jupiter assist, the same flyby at Pluto. Strap a human-rated cabin onto it in your mind. Best case, you are signing up for roughly a decade in deep space one way, for a mission that does not stop, does not land, and does not come back. You launch, you spend around 9 or 10 years in cruise, and then you get just a few hours in the Pluto system at high speed before the ship flies on into deeper space forever. For a human mission, that profile is extremely unattractive. No chance to brake and go into orbit. No chance to land and explore the surface over months or years. No return leg unless you bolt on an entire second propulsion system and even more propellant, which New Horizons did not carry. It shows you how harsh the reality is. Even our most extreme, successful Pluto trajectory is still basically a one-shot dart that just zooms past. So what does New Horizons actually prove about your original question? It quietly gives you a baseline. With current chemical rocket technology, plus a carefully planned gravity assist from Jupiter, you can get a small uncrewed spacecraft from Earth to Pluto in about a decade. As long as you are okay with never slowing down. That's the key phrase, never slowing down. You put almost all your effort into the initial push. You get a free extra boost from a giant planet. You coast for nearly 10 years. And when you arrive, you are still going so fast that stopping is not an option. If you now demand something much harder, like sending humans, and not just flying by, but actually arriving at Pluto and stopping there, the bar jumps dramatically. You would need an engine that can not only reach New Horizons class speeds, but also deliver another chunk of velocity in reverse to brake when you reach the dwarf planet. That means tens of thousands of miles per hour of extra speed change on arrival, and you have to carry the fuel for that braking all the way from Earth. With pure chemical rockets, that becomes a nightmare of fuel mass, staging and cost. That is why when you look at New Horizons with clear eyes, the message is a bit ominous. Pluto, with today's chemical rockets and clever gravity assists, is about a decade for a small robot that never stops. Turning that into a safe crewed mission that can brake, orbit, maybe land and come home, would require a propulsion system that makes New Horizons look slow and inefficient by comparison. And if the fastest, most optimized robotic shot we have still needs 9.5 years, what happens when you drop down to speeds that are closer to what a large, heavy human ship could realistically maintain? Here's the part that really breaks your sense of distance. When you drop down to speeds that feel normal and ask how long Pluto would take at human speeds, the number stops sounding like a trip and starts sounding like a punishment. Start with something you know, a car on a highway. Take Pluto's average distance from the Sun, about 3.7 billion miles, and picture a steady 60 miles per hour. All day, every day, no traffic, no stops. You take that distance, 3.7 billion miles, and split it by 60 miles every hour. You land in the range of more than 60 million hours on the road. Turn that into years, and you're sitting around 7,000 years of non-stop driving. 1,000 years at highway speed just to cover the average Pluto distance once. Every mile sign you've ever seen, every next town in 10 miles you've ever felt bored by, all of that becomes meaningless. Because at this scale you're not counting days or months or lifetimes, you're counting entire slices of human history. So the obvious question is, does going faster in a way that still feels normal, like an airliner instead of a car, actually fix this? Or does it just make the nightmare slightly less bad? Step up to a commercial jet, cruising at around 500 miles per hour. Same 3.7 billion miles, now divided by 500. You are still left with millions of hours of flight, which turns into something like 800 to 900 years. Think about that. If people had loaded a jet and pointed it toward Pluto back when the Vikings were reaching North America, that plane, flying this whole time at cruise speed, would still not have arrived today. You can swap out the car for a jet, you can go almost 10 times faster, and you're still trapped on a timeline that's close to 1,000 years. At this point you might think, alright, that's not fair, cars and planes are not space hardware, give it a real shot with actual orbital speeds, so let's do that. Look at the International Space Station. It moves at about 17,500 miles per hour around Earth. At that speed, it can circle the entire planet in about 90 minutes. That sounds insanely fast, and in low Earth orbit it is. Now, push that speed out into deep space. Use it as your cruise speed over that same 3.7 billion mile distance. You take the miles, divide by 17,500 miles per hour, and you get on the order of 170,000 hours of travel. Turn that into years, and you end up at roughly 24 years. Here is what that really means. You could be born the day the ship leaves, grow up, finish school, get a job, maybe start a family, and that ISS speed ship would still be on its way to Pluto. You have finally dropped the timescale from thousands of years down into a single human working lifetime. But it is still long enough that the mission would be a defining event for everyone who flies it. You do not go to Pluto for a quick tour, you sign away decades. So the next question is obvious. If ISS speed still traps you in decades, what happens if you push closer to the New Horizons regime, those 30,000 plus mile per hour numbers that already got a probe there in under 10 years? Near Pluto, New Horizons was moving at roughly 30,800 miles per hour relative to the dwarf planet. Use that as a rough constant cruise speed over a shorter Earth-Pluto distance, say around 3 billion miles for a favourable alignment. You divide 3 billion miles by about 30,000 miles per hour, and you land in the ballpark of a little over 11 years. That lines up with what the real mission showed you, a 9.5-year trip with a powerful launch and a gravity assist, roughly an 11 to 12-year raw distance divided by speed number, once you ignore the messy details of acceleration and course correction. And that is the key point. Real missions never get to just pick a speed and hold it from second one. They have to burn hard at launch, coast for years while the sun's gravity curves their path, and then thread the needle at the destination. The fact that New Horizons covered that whole journeys in under 10 years is not just fine, it is impressive, because it's basically sitting right up against what the simple math says is possible for that distance and speed range. So after you see all of that, there is one more trap your brain tries to fall into, and you need to shut it down. You might be thinking, these times are huge because you keep talking about orbits. Why not just go in a straight line and ignore all the extra motion? On the surface, that sounds reasonable. In reality, it is where your Earth-based intuition fails completely. Here is the straight answer: you're already moving. Earth is orbiting the Sun at around 67,000 miles per hour. Pluto is also orbiting on its longer stretched out path. When you launch a rocket, you're not starting from zero, you're adding speed on top of Earth's existing orbital motion. Everything you do is happening inside the sun's gravity well, so straight line is not a mode you get to choose. Your path is always curved, your velocity is always being bent, and your target is always shifting its position while you're in transit. Most of your energy is not spent just pushing forward, it is spent changing your direction relative to the sun, changing your orbit. When you leave Earth, you are not stepping off a platform. You are jumping from one racetrack lane to another, higher, slower lane, and then maybe to an even higher, slower lane farther out where Pluto runs. That is why orbital mechanics is sometimes called orbital billiards. You are knocking yourself from one orbit into another, using burns and gravity assists, not simply pointing at a fixed point and flooring it. So when you boil this section down, here is what you really learn. At human scale speeds, the universe does not care how fast your life feels. 60 miles per hour, 7,000 years. 500 miles per hour, close to 1,000 years. 17,500 miles per hour, around 24 years. 30,000 plus miles per hour, still around a decade or more. And the shortcut of a straight line does not exist, because you are always in motion around the sun, always curving, always spending precious energy to shift direction rather than just slam forward. And that tension sets up the next step. If normal human speeds and even our best current robotic speeds still lock you into decades, what happens when you try to push harder and you run straight into the limits of acceleration, G-forces, and the uncomfortable fact that your body is a soft, fragile piece of biology trying to ride a very hard, unforgiving rocket? You might think the fix is simple. If Pluto is far away, just push the throttle harder and keep pushing until you're going insanely fast. The problem is, your body does not care about your big goals. It only cares about how hard you're being pushed into your seat and for how long. To get a ship from standing still up to New Horizon class speeds, tens of thousands of miles per hour, you have to accelerate it. That means you have to choose an acceleration your crew can actually live with. For long stretches, you're basically capped at around 1g, the same pull you feel from Earth's gravity, about 32 feet per second every second. At 1g, the numbers look amazing on paper. Your speed climbs very quickly. In just a few hours, you could rack up tens of thousands of miles per hour. So why don't we just do that? Because at our current tech level, doing that with a big, heavy, human-rated ship means burning absolutely absurd amounts of propellant. Every extra second at 1g costs you fuel. The faster you want to go, and the longer you want to keep accelerating, the more of your ship has to be nothing but fuel tanks. That is the rocket equation biting you. You try to push harder and longer, and the ship gets heavier and bulkier, which then demands even more fuel, which makes it heavier again. Very fast, very long 1g burns are something our chemical rockets simply cannot support for a Pluto run. So maybe you think, alright, if 1g is the comfortable limit, what happens if you push past comfort and just accept that it will feel rough? Human bodies can handle more than 1g, right? Yes, for a while. Fighter pilots can survive 6 to 9g for short bursts with pressure suits and training, and even then they are right on the edge of blacking out. But you cannot strap a Pluto crew into their seats at 6g for hours or days. At those loads, blood gets pulled out of your brain, your organs shift, your spine is under constant compression. You get vision problems, you pass out, you take real damage. That leaves you with only 2 realistic playbooks for a human Pluto ship. Option 1, you take it very slow, at fractions of a g, maybe a tenth of a g or less, stretched over days or weeks. That feels fine physically, but it means your acceleration phase alone can last a long time, and you are burning fuel that whole stretch. Option 2, which is what we actually do today, is you use short, high-powered burns near the start to boost your speed, then cut the engines and coast for years, just like New Horizons did, with only tiny course corrections along the way. Either way, your average acceleration over the whole trip is tiny, even if the initial push feels dramatic, and there's a bigger catch. Going fast is only half the story. If you actually want to arrive at Pluto and not just blast past it and disappear into the Kuiper belt, you have to slow down again. This is the flip and brake problem. For a truly aggressive profile, you would spend the first half of the journey speeding up, constantly increasing your speed. Then at the midpoint, you flip the ship around and spend the second half firing the engines in the opposite direction to slow down. Half the distance is spent building speed, half is spent cancelling it. On paper, a 1G there, 1G back kind of trip could get you across the solar system surprisingly quickly. But to do that, your engine has to deliver huge thrust for a very long time, and your ship has to carry enough propellant to both accelerate and decelerate at that rate. With chemical rockets, that is completely out of reach. The fuel mass explodes. You don't just need a better rocket, you need a different class of propulsion system entirely. So right away, for real human trips to Pluto, you are pushed toward profiles where you give up on constant acceleration dreams and accept long coasts and long mission times. While all of this slow, careful changing of your velocity vector is happening, there is another background problem that does not care about your budget or your plans: radiation. Once you leave Earth's magnetic field, you lose most of the natural shield that protects you from charged particles coming from the sun and from deep space. Out there, your ship and your body are exposed to cosmic rays and solar storms almost all the time. The International Space Station deals with some of this, but it still sits inside part of Earth's magnetic protection, and missions there last months, not decades. A 10-year trip to Pluto means 10 years in that harsher environment. Every year you're out there, your cumulative radiation dose climbs. Electronics degrade, cancer risk for the crew creeps up. You can add shielding, but shielding is heavy. And again, heavy means more fuel, more thrust, more cost. So your go gently for a long time plan clashes directly with limit the time humans spend bathing in radiation. Then there is the quiet killer of every long mission: life support. Every extra year you add to your timeline forces you to ship more mass just to keep people alive. More food, more water, more oxygen, more spare parts for recycling systems, more medical supplies, more redundancy in case something breaks. You can and should recycle a lot of it, but recycling systems themselves need hardware, pipes, filters, tanks, and they wear out. On a mission measured in decades, you are not just resupplying, you are carrying a small, repairable, closed ecosystem. This is where the vicious loop really locks in. You say, we will accelerate more gently to keep g-forces low and fuel needs manageable. That stretches the trip time. The longer trip time means more life support mass. More life support mass demands more propellant to push it. More propellant means a bigger ship, which again increases the propellant you need to maneuver it. Meanwhile, the longer you're out there, the more radiation dose your crew absorbs, so you want more shielding, which adds, you guessed it, more mass. Put this together, and you get a simple but harsh conclusion. With today's engines and materials, human trips to Pluto are trapped in the decade range, not the few-year range. You cannot just floor it because your body cannot tolerate the g-forces for long, your rockets cannot sustain that kind of acceleration with the needed mass. And your life support and radiation problems grow every time you try to smooth things out by adding extra years of gentle flight. And here is the kicker. Even if you solved every biological problem perfectly, your heart, your bones, your radiation shielding, you still would not get to pick any path you want. You are still locked into the rules of orbital mechanics, which say you are not shooting at Pluto itself, you are shooting at its orbit, on a path that can easily stretch into decades if you try to save fuel. So what happens when you stop thinking in terms of just go faster and start looking at the actual orbits and the so-called cheap ways to move between them? Here's the next twist you have to deal with. When you say go to Pluto, you are not actually aiming at Pluto itself. You're aiming at its orbit. And that detail quietly wrecks a lot of the shortcuts your brain wants to use. The standard cheap way to move a spacecraft between two circular orbits around the Sun is something called a Hohmann transfer. In plain language, you start in one almost circular path. You fire your engine once to stretch that path into a long ellipse, and that ellipse just touches your starting orbit at one end and your target orbit at the other. You then coast along that ellipse until you reach the far side, and there you fire your engine again to settle into the new orbit. From Earth's path, about 93 million miles from the Sun, to Pluto's average path, About 3.7 billion miles out, that ellipse is extreme. You're going from an inner track near the warm centre to a far, cold track at the edge. The whole idea of a Hohmann transfer is to save fuel. You accept a long, slow climb outward in exchange for the smallest possible push from your engines. The sun's gravity does most of the work, bending your path. That sounds nice until you look at the timeline. When you run the numbers for a low-energy Hohmann transfer from near-Earth's orbit to the region of Pluto's orbit, you do not get 10 years or 15 years, you get decades. You're taking an enormous fraction of Pluto's 248-year orbital period just to creep up that energy hill. For a frozen robot that does not age, decades of cruise time can be acceptable if the science payoff is big enough. For a human crew, see you in 30 or 35 years when you reach Pluto's distance is not a serious offer. By the time you arrive, your career is over, your body has taken huge radiation doses, and your life has been dominated by a single trip. So right away, you can see why the pure, cheap and slow path is a non-starter for people. That is why New Horizons did not use a pure Hohmann transfer. The team chose a higher energy trajectory. They launched the spacecraft on a very fast path right out of Earth's gravity well, then aimed it towards Jupiter for a gravity assist, bending and boosting its orbit again, and finally sent it on a more direct shot to Pluto's region. That choice cut the travel time down to under 10 years. The trade-off was cost and flexibility. You need a more powerful launch, you accept higher relative speed at Pluto, and you give up the ability to slow down and go into orbit around the dwarf planet. You get a fast flyby, not a leisurely controlled arrival. Now think about what that means for a crewed mission. If the robotic, no-stopping version already needs more energy than a clean Hohmann to keep the time under a decade, a human ship, which you would want to move faster than a 30-year cruise but slower than a crash flyby, has to push even harder. You're trying to keep the timeline under a working lifetime, 10 to 20 years round trip instead of 30 plus one way, but every time you push for a shorter cruise, the required energy spikes. With chemical rockets, you quickly hit a wall where the fuel mass becomes ridiculous. There is another layer of constraint here that you cannot ignore: launch windows. Earth and Pluto are circling the Sun at very different distances and speeds. On top of that, if you're using Jupiter for a gravity assist, Jupiter has its own position and timing. You only get good geometries where the angles and distances line up for an efficient path at certain times. New Horizons had its launch in early 2006 for a reason. That window gave a clean shot to Jupiter, then from Jupiter to Pluto at the right moment. If you miss that kind of window, you don't just add a couple of months. You can be pushed back by years, waiting for Earth, Jupiter, and Pluto to fall into a favourable pattern again. The cosmos is running on geometry and orbital periods, and it does not care about your fiscal year or your launchpad schedule. So when you ask how long would it take to go to Pluto, you have to quietly include plus possibly several years of waiting for the right alignment before you even leave the ground. And even after launch, the clock is not just ticking on the pure distance divided by speed part. There are hidden time costs built into every serious mission. In the first months, you are commissioning the spacecraft, carefully checking every system after the violence of launch. You are calibrating instruments, adjusting antenna pointing, verifying power systems. Throughout the trip, you are doing mid-course correction burns to clean up the trajectory, because no launch is perfect and tiny errors grow into huge misses over billions of miles. On a long cruise like New Horizons, you also put the spacecraft into hibernation modes for extended stretches to save power and reduce wear on hardware, then wake it up for checkouts and science campaigns. Each wake-up, each test, each trajectory tweak takes planning time, ground control time, and often slows down other activities. From the outside, the 9.5 years to Pluto might sound like 9.5 years of nothing happening. In reality, every year on that timeline has a job, a set of tasks, and a risk budget. For humans, all of those mission phases get even more complicated. Your commissioning phase is also people adapting to deep space, verifying life support, shaking out any bugs in long-duration habitat systems, Your mid-course corrections are not just small burns, they are moments where any failure could threaten the crew. Your hibernation is not literally turning the crew off, it is long stretches of routine operations where boredom, stress and isolation become real factors. So the simple travel time hides a huge amount of process. Put all of this together, and orbital mechanics does not just tell you how far and how fast. It tells you that the cheapest path is often decades, that shortening the trip demands huge energy, that you only get good paths during tight windows, and that there is a constant tax in the form of system checks, corrections, and planning overhead. A Pluto timeline is not just a single number. It is a stack of constraints that all push you toward longer than you want. So the natural next step is to ask, given all of these orbital realities, what can you actually squeeze out of the rockets we have now? How far can today's chemical rockets really push a human Pluto mission before the fuel, mass, and cost all explode? Here's the uncomfortable question you have to face now. If you squeeze everything you can out of the rockets we already know how to build, how far does that really get you toward a human trip to Pluto, and where does the physics just say no more? Start with what chemical rockets can actually do today. Look at vehicles in the same class as Atlas V, Falcon Heavy, the Space Launch System. When you stack them with upper stages and push them hard, they can give a spacecraft departure speeds in the range of tens of thousands of miles per hour, relative to Earth. New Horizons is the clean proof. Its Earth escape speed, about 36,000 miles per hour, is a solid benchmark for what a heavy launcher plus upper stages can do for a modest robotic payload. That's not a weak number. 36,000 miles per hour is enough to leave Earth's gravity behind and head for the outer solar system. So here's the key point. From a pure can chemistry throw something at Pluto perspective, the answer is already yes, we've done it. But look at what that actually buys you. It gets a small probe on a one-way, no-braking, no-return trajectory that still takes almost a decade to reach a flyby. Now think about what you want from a crewed mission. You don't just want to hit Pluto and keep going. You want to arrive and slow down enough to enter orbit, or even land. That changes the energy budget completely. You still need the initial tens of thousands of miles per hour just to climb out of the inner solar system and cross those billions of miles. But now, on top of that, you need another set of burns at the far end to cancel out a huge amount of that speed so you don't just streak through the system and vanish. In plain language, you need tens of thousands of miles per hour of extra speed change available when you get there. Engineers call this delta V, total change in velocity your system can produce. For a Pluto mission that wants to arrive and stop, your delta V has to cover both the departure and the braking. With pure chemical propulsion, every bit of that performance comes from burning propellant, which means you need to haul enormous amounts of fuel all the way from Earth to Pluto, just so you can fire it at the end. And here's the catch that locks you in. The more fuel you want to have waiting for you near Pluto, the more fuel you have to launch at the start to push that fuel, and the tanks that hold it, and the structure that supports those tanks. You get into a spiral where fuel mass generates more fuel mass. That's not a design choice, that's baked into the Tsiolkovsky rocket equation, the basic math that connects exhaust speed, fuel mass, and how much you can change your velocity. So you start reaching for tricks, because you don't like what the basic numbers are telling you. You can stack multiple stages, dropping empty tanks as you go to shed weight. You can launch pieces separately and assemble your Pluto ship in orbit. You can talk about in-space refueling or pre-positioning propellant depots somewhere between here and the outer solar system. All of these are tools you should use for a mission this demanding, but there is a hard truth under them. None of them change the core relationship. Every extra pound of propellant you plan to use later still has to be pushed by some other propellant earlier. That's why when people say the rocket equation wall, Pluto is exactly the kind of target they're talking about. Chemically driven missions to Pluto that arrive and stop are not blocked by physics in the sense of impossible. They are blocked by practicality. The mass grows, the number of launches grows, the complexity grows, until you are staring at a project so big and expensive that it starts to look like a national or even global mega program. So what does that mean in actual time numbers for a human ship if you really throw everything we have at the problem? Picture using something in the Space Launch System class, or even more advanced heavy lift rockets, not just once but many times. You assemble a big interplanetary vehicle in orbit. You use aggressive staging, big upper stages, maybe even on-orbit refueling to top everything off. You do not fly a gentle low-energy Hohmann. You pick a higher-energy trajectory to keep the trip from turning into a multi-decade crawl. Even with all of that, for a ship massive enough to carry humans, serious shielding, real-life support and enough chemical propellant to break at Pluto, you are likely still talking about one-way travel times in the 15 to 20-year range. Maybe you shave it down if you accept a more dangerous, very high-energy profile, with thinner safety margins and more risk if anything goes wrong. But those kinds of numbers, 15 to 20 years one way, sit right at the bleeding edge of what chemistry can even dream about for a mission that actually slows down. And notice how ugly that looks when you stack everything. You're not just designing one giant rocket, you're designing multiple heavy launches, orbital assembly, massive propellant management in space, and then a ship that has to survive decades of deep space hazards with people on board. All of it is chained to engines that, in the end, are still just burning chemical propellant and throwing it out the back at a few miles per second. That's why the conclusion here is not we can't do it. It's we can do it, but not in any way that looks clean or sane. New Horizons has already proven that chemical rockets can fling hardware past Pluto in about a decade. If you are clever with trajectory and gravity assists, chemistry is good enough to fire a small dart across the solar system. But when you ask for a crewed mission that arrives, has propellant left to break, and maybe has enough performance to leave again, the picture changes. Now you're staring at mission durations still measured in decades, launch campaigns that involve fleets of heavy rockets, and total costs that would crush any space budget we've ever had. You're not just going to Pluto. You're committing to a single project that could dominate spaceflight spending for a generation. So if chemistry alone traps you in decades and brutal logistics, where do you look next? You start searching for a way to cheat the energy problem without paying for all of it in fuel, and that means turning the solar system itself into part of your engine, with gravity assists and more exotic propulsion layered on top. You already know chemical rockets alone make Pluto a decade or multi-decade problem. So the obvious move is to ask, can you steal some of the speed you need from the planets themselves instead of paying for all of it in fuel? That's what gravity assists really are. Not a trick of visuals, but a straight trade of motion between your spacecraft and a massive body like Jupiter. Here's how it actually works in simple terms. Take a probe headed for Jupiter. Far from the planet, it is moving around the Sun on its own orbit. Closer in, Jupiter's gravity starts to bend its path. If you aim the trajectory so the spacecraft passes behind Jupiter, relative to the planet's direction of motion, the probe falls in, speeds up, swings around and then climbs back out. In Jupiter's own frame, the speed before and after are almost the same, but Jupiter is also moving around the Sun at its own high speed. Seen from the Sun's frame, the spacecraft leaves with a different velocity than it had before. It has gained or lost tens of thousands of miles per hour, and Jupiter has lost or gained a tiny amount of its orbital energy. You have literally traded a microscopic slice of Jupiter's angular momentum for a big boost to yours. New Horizons used this for real. After its fast launch in 2006, it reached Jupiter in early 2007. It flew through the planet's gravity field on a carefully planned path. That single flyby increased its speed by roughly 9,000 miles per hour relative to the Sun and bent its trajectory onto a cleaner line toward Pluto. That one maneuver cut about 3 years off the cruise. Without the Jupiter assist, you would either accept a travel time closer to 12 years or pay for it with a significantly bigger launch vehicle and more propellant. So right away you can see how valuable this free speed can be for the outer solar system. Once you understand that, the next question is obvious. Why stop at one assist? In principle, mission designers can chain multiple flybys together. You can build paths like Earth to Venus, back to Earth, then out to Jupiter, then maybe Saturn, and finally onto Pluto. At each encounter, you can tune the flyby altitude and angle to add or remove speed and to reorient the trajectory. It is literally possible to design a path where the spacecraft bounces around the inner and outer planets, picking up increments of velocity at each step. But each added flyby has a cost. It adds complexity because the navigation and timing have to be nearly perfect. Any small error at one flyby propagates into a larger miss at the next. It adds risk, because you often have to pass close to powerful radiation belts or deep into a planet's gravity well. And most importantly for your question, it adds time. Every extra loop to Venus or Earth or Saturn stretches the path. You're trading fewer propellant burns for more calendar years. For a one-off Pluto mission, especially a robotic one, the sweet spot is usually 1 or 2 major assists, for example direct to Jupiter, then on to Pluto, not some 5-planet odyssey that takes half a century to complete. This is where you have to separate what is clever for a robot from what is acceptable for a crew. Some of the most aggressive trajectories we've ever flown are simply not survivable for humans with current materials. A good example is the Parker Solar Probe. It dives extremely close to the Sun, using multiple Venus flybys to gradually shrink its orbit. At its closest passes, it reaches speeds around 430,000 miles per hour. That's roughly 120 miles every second. Those numbers are what make people say space is small if you go fast enough, and they're not wrong on a physics level. But look at the environment Parker flies through to get that speed. Near the Sun, the heat and radiation levels are extreme. The probe's heat shield sees temperatures of thousands of degrees Fahrenheit. Electronics are buried behind thick protection. A human crew in anything like our current spacecraft would be cooked and irradiated long before they ever reach those velocities. The same is true at a smaller scale for deep dives into the intense radiation belts around giant planets like Jupiter. Robots can tolerate paths and exposure levels that people simply cannot. So you get a trade that looks like this. For robots, gravity assists are a major reason Pluto missions can be only 10 years instead of 20 or 30. You can accept a deep Jupiter flyby, an awkward extra loop around the Sun, or a long chain of planetary encounters, because nobody is on board. The probe can sit in a harsh radiation environment, its systems can be hardened, and if it fails, it's a loss of hardware, not lives. For humans, you would still use gravity assists. Ignoring that free energy would be wasteful. You might accept a carefully designed pass by Jupiter, or maybe Saturn, to trim your fuel needs and time, but every assist you add tacks on months to a year or more of extra flight time. Each extra year in deep space is another year of radiation exposure, more wear on life support systems, more psychological strain on the crew, and more chance for something to go wrong. This is the bottom line. Gravity assists give you speed without burning fuel, but they are not truly free. You pay for them in geometry, in time, and in risk. You have to hit narrow launch windows. You have to thread a moving 3-dimensional target at each planet. You have to accept passes through harsher environments if you want the biggest boosts. For a small, hardened robot like New Horizons, that trade is fantastic. For a crewed Pluto mission, those free pushes help, but they do not suddenly turn a decade-scale mission into a quick hop. They just shift you from completely impossible with chemistry to barely possible, but still very long and very hard. And once you accept that gravity and clever trajectories can only take you so far, you are forced to look at propulsion systems that work very differently from big chemical burns at the start and end. You start asking, what about engines that push gently, almost all the time building up speed over years with very little propellant? And could those finally pull a Pluto trip down into something closer to a single decade, even if you want to stop when you get there? Ion engines sound like sci-fi, but they're already flying, and they attack the Pluto problem from a completely different angle. Instead of one huge shove at the start and then years of coasting, you accept very weak thrust, and you just keep pushing day after day, year after year, until the total speed you've built up is something chemical rockets would struggle to match. Here's the key difference in how they work. A chemical rocket burns fuel and throws hot gas out the back at a few miles per second. An ion engine uses electric power to strip electrons off atoms, usually xenon, and then uses electric fields to fling those charged ions out the back at tens of miles per second. The exhaust is way faster. That means for every pound of propellant, you can get a much bigger total change in speed. The catch is the thrust. It is tiny, literally comparable to the weight of a sheet of paper resting on your hand. At any single moment, it feels like nothing. But ion engines can run not for minutes, but for months or years. Over that kind of timescale, that almost nothing force adds up to real deep space speeds. So you might ask, is this just a neat idea on a whiteboard, or have we actually done this? We have. NASA's Dawn spacecraft is the best real example. Dawn used ion engines to travel around the inner solar system, orbit the asteroid Vesta, leave Vesta, and then enter orbit around the dwarf planet Ceres. Over its mission, Dawn changed its speed by well over 10,000 miles per hour using only a few hundred pounds of xenon propellant. That is a big deal. A chemical rocket burning a few hundred pounds of propellant would barely move the needle on a deep space mission like that. Dawn showed in hardware that long-duration high-delta V missions with ion drives are not theory, they're a working tool. Once you see that, the obvious question is, could you point that same technology outward toward Pluto and do better than a one-shot flyby? In principle, yes. An ion-driven Pluto mission could look very different from New Horizons. Instead of one big burn, a gravity assist, and a decade of coasting, you could accelerate gently for years, always adding a little more speed. At some point you flip the spacecraft, and you brake for years, slowly cancelling that speed. The payoff is that when you reach Pluto, you are not screaming past at 30,000 miles per hour with no way to stop. You could arrive with the ability to enter orbit and stay there, mapping the system for years. Time-wise, you're probably looking at something like 10 to 15 years total travel with current level ion tech scaled up and aimed at the outer solar system. That's similar or slightly longer than New Horizons flight time, but with a completely different end result. An orbiter, not a flyby. And crucially, you get that while carrying much less propellant than a pure chemical orbiter would need. You're spending your budget on time and power, not on giant tanks of fuel. So what's the catch that stops us from doing this tomorrow? Power. Ion engines need electricity. Dawn's engines were powered by solar panels delivering a few kilowatts near the inner solar system. That works fine around Mars and the asteroid belt. But as you go outward, sunlight drops fast. By the time you reach Pluto's distance, sunlight is only about 1/15,000th as strong as it is near Earth. Panels big enough to power high-thrust ion engines out of Era would be ridiculously huge and heavy and would still barely trickle out power. That pushes you straight into nuclear territory. If you want ion drives to keep working well beyond Jupiter, you need a power source that does not care about sunlight. That means radioisotope generators, which use the heat from decaying radioactive material, or full-on space reactors, compact nuclear power plants that can deliver tens or hundreds of kilowatts continuously. For a serious Pluto orbiter, especially one that wants to do years of ion thrusting, you're talking about significant nuclear power levels, not the tiny wattage of a deep space probe's radioisotope battery. Now, ask the harder version of the question, could you do this with humans on board? On paper, ion drives are very attractive for crewed missions. They have high specific impulse, which just means they use propellant very efficiently. They can deliver continuous, gentle acceleration, which is exactly what you want for long trips where you don't want to hit people with big G-forces, and they make the whole trip feel more ship-like, always adjusting your speed a bit, instead of just being a stone thrown once and left to coast. But to make that happen, you have to scale everything up by a huge factor. Dawn used a few kilowatts of power. A crewed Pluto ship with ion propulsion would likely need power in the megawatt range to produce enough thrust to move a heavy, shielded habitat, life support systems, and all the other hardware. That is roughly 1,000 times more power, delivered continuously in deep space for years. That means a serious nuclear reactor in space with all the shielding and safety systems that go with it. Then you hit the human side. You have to shield the crew not just from cosmic rays and solar storms, but also from the radiation of the reactor itself. You have to deal with waste heat from both the reactor and the engines, which is much harder to dump into space than it is on Earth. You have to design a ship where the crew can live for a decade or more, while a massive high-power electric propulsion system runs not far away. That is a hard engineering problem, but not a fantasy-level one. If you could solve those issues, if you can fly a megawatt-class nuclear electric propulsion system safely, keep it running for many years, and manage the radiation and heat, then the Pluto picture changes. You stop talking about 10 years to a flyby and start talking about something like under 10 years to arrive and stop. Suddenly, an 8 or 9 year outbound trip with a real orbit insertion burn at the end looks possible. It is still long, it is still harsh, but now you have a ship that can actually slow down, stay, and maybe even leave again. So ion drives give you a clear message. With small solar-powered engines, they already let us do things in the inner solar system that chemical rockets struggle to match. With big nuclear-powered engines, they could turn Pluto from a one-shot flyby target into a place you can truly visit and orbit in under a decade. But to actually make that real for humans, you need to step into nuclear propulsion territory in a serious way. And that leads straight into the next question. What happens when you stop just using nuclear power for electricity and start using it directly as the engine itself? Chemical rockets are already at their limit, and they still leave Pluto sitting decades away. At some point you stop asking for a bigger fuel tank and start asking a harder question. Why are we still burning chemistry when we could be burning atoms? Start with nuclear thermal rockets, NTRS. In this setup, you don't change the basic rocket idea. You still throw mass out the back for thrust, but you change what heats that mass. Instead of a chemical flame, you use a nuclear reactor. Liquid hydrogen flows through a reactor core, gets heated to thousands of degrees, and blasts out the nozzle as super hot gas. That one change roughly doubles or even triples the specific impulse compared to the best chemical engines. In normal language, for the same pound of propellant, you get 2 to 3 times the kick. On paper, that does not sound like magic. Doubling or tripling something is not a 1,000-fold jump, but in rocket math, that kind of exhaust velocity boost is huge. Every bit of extra efficiency means you either get more total change in speed from the same fuel mass, or you can carry less fuel for the same mission performance. When you are talking about deep space missions that need tens of thousands of miles per hour of total speed change, that difference compounds fast. So what does that really mean for Pluto trip time? If you double your exhaust velocity, the same propellant suddenly buys you much more delta V, much more total speed budget. You can spend that bonus in 2 ways. You can use it to push harder and cut years off your cruise, or you can use it to carry the extra propellant and engine power you need to brake at Pluto, instead of just flying by. Simulations of NTR-powered outer planet missions show that depending on the profile, you can cut trip times by something like 30 to 50% compared to an all-chemical design. Translate that into numbers you care about. Take a 10-year robotic Pluto mission based on aggressive chemical and gravity assists. Swap in nuclear thermal propulsion, keep everything else similar, and suddenly a 6 to 7 year arrival starts to look reasonable on paper. For a slower, stop-and-orbit mission that might have taken 20 years with chemistry, you could bring it down toward 10 to 15. The exact numbers depend on staging, payload mass, and trajectory, but the pattern is clear. NTRS are one of the first technologies that don't just squeeze the margins, they noticeably move the calendar. Then there's the cousin approach, nuclear electric propulsion. Here, the reactor is not heating the propellant directly. Instead, it acts like a power plant. A compact space reactor produces electricity, and that power feeds high-efficiency electric thrusters, ion engines or Hall effect thrusters, the kind you just heard about. Now your exhaust is moving at tens of miles per second like Dawn's thrusters, but you're no longer limited by weak sunlight. You can run those engines almost anywhere in the solar system as long as the reactor stays healthy. This is exactly the combination a fast-ish Pluto orbiter or crewed ship would want. A nuclear thermal system gives you big, strong burns when you need them, such as leaving Earth or braking hard at Pluto. A nuclear electric system gives you continuous, efficient thrust during the long cruise, slowly stacking up speed without guzzling propellant. You can even imagine hybrid mission profiles where you use NTRS for the heavy lifting at the start and end, and NEP, nuclear electric propulsion, to trim the trajectory and cut down the coast phase in the middle. The key question then is this all just concept art, or is any of it grounded in real hardware and real programs? There is history here. Back in the 1960s and 70s, the United States tested nuclear thermal engines on the ground under programs like NERVA. Those tests showed that you can build a working reactor-based rocket engine with performance well above chemical designs. They were never flown, mostly for budget reasons, not because the physics failed. Today, modern versions of those ideas have come back into serious discussion for Mars transport and deep space cargo. Agencies are again funding studies and even hardware work on nuclear thermal propulsion as a near-future technology, not a sci-fi prop. If systems like that actually make it to flight status, your Pluto numbers change from pure speculation to something you can say out loud without flinching. A robotic Pluto orbiter powered by nuclear thermal or nuclear electric propulsion starts to land in the 5 to 8 year arrival window, depending on how aggressive you are. You leave Earth, accelerate harder and longer than a chemical probe could, and then still have the delta V left to slow down and capture into orbit around Pluto or its moons. For a crewed mission, you're still chained to life support, shielding, and all the human factors you've heard about. But now your travel times start to look like 10 to 15 years round trip instead of 20 plus just to get there. That's not a quick vacation, but it is a time frame you can describe as within half a working lifetime, instead of this will eat your entire existence. Of course, none of this is free. Once you say nuclear, you've swapped one kind of difficulty for another. Technically, you have to design reactors that can survive launch, operate safely in space for years or decades, and handle all the heat and radiation they produce. You need to keep the crew far enough away, or shielded well enough that the reactor is not adding to their already serious cosmic radiation load. You have to deal with failure modes. What happens if a launch vehicle fails and drops a nuclear stage back onto Earth? Or if a reactor malfunctions in orbit? On top of that, you have public perception challenges. Launching nuclear material into space makes people nervous, with some justification. Any serious nuclear propulsion program has to convince regulators, governments, and the public that the risk is low enough and the payoff is high enough to be worth it. That slows development. It adds layers of testing, safety reviews, and international discussions before you ever light the first reactor in space. But pull back to the core question you started with. How long would it really take us to go to Pluto? Up to this point, every realistic human timeline has been decades by default. Chemical propulsion plus gravity tricks keeps you in that regime. Ion drives without nuclear power are limited by weak sunlight. Gravity assists buy you speed but cost you time and risk. Nuclear thermal and nuclear electric systems are the first tools that change the shape of the answer. They do not make Pluto a weekend trip. They do not turn it into a Mars-style mission you can fit into a few years. But they are the point where a serious engineer can look you in the eye and say, if we fund this, build it and accept the risk, we can talk about humans reaching Pluto and coming back in a timescale that fits inside one person's career. Once you accept that, another question opens up in front of you. If nuclear engines can cut outer planet trips almost in half, what happens when you stop looking at engine design and start asking about the absolute speed limits we've already proven in space, like the Parker Solar Probe's record-breaking velocity, and whether that kind of speed could ever be aimed at Pluto with people on board? Here's a number that should completely reset your idea of fast in space. Right now, the speed record for any human-made object is about 430,000 miles per hour, and we've already done it. NASA's Parker Solar Probe reaches that speed when it skims just a few million miles above the sun's surface. That's roughly 118 miles every second. At that pace, you could cross the entire United States from New York to Los Angeles in under half a minute. Nothing we've ever built has moved faster, and it proves that, under the right conditions, insane velocities are not just theory, So the obvious question is this. If we can push a spacecraft of 430,000 miles per hour, what would that do to a Pluto trip if you could somehow aim that speed in the right direction? Take a rough Earth-Pluto distance of around 3 billion miles. Pick that as a working average for a favourable alignment. Divide that distance by 430,000 miles per hour, and you land in the range of 8,000 hours of travel. Turn that into days and months, and you're talking about something like 11 months, just under a year. Suddenly Pluto drops from a 10 or 20-year ordeal down into this year's cruise. That still doesn't beat light, which makes the Sun-Pluto trip in a few hours, but it does something important. It moves your ship into the same general ballpark of fast that light occupies. Instead of crawling compared to photons, you're now a bit slower, but not absurdly slower. On a simple distance divided by speed level, 430,000 miles per hour makes Pluto feel like a long mission, not a life sentence. So if the math looks that good, why isn't anyone seriously proposing to just do a Parker solar probe and then turn toward Pluto? The reason is simple and harsh. Parker gets that speed by doing something that would kill a human crew and destroy any normal spacecraft. It doesn't start that fast. It builds speed by repeatedly falling deep into the Sun's gravity well, using a series of Venus flybys to drop its closest approach lower and lower. Each dive brings it closer to the Sun, where gravity pulls harder and orbital speeds climb. Near its closest passes, the thermal environment is brutal. The heat shield faces temperatures on the order of about 2,500 degrees Fahrenheit. The spacecraft hides in the tiny shadow behind that shield. Everything is designed specifically to survive a blast furnace environment that would vaporize normal materials. No existing human spacecraft and no current life support system can keep a crew alive anywhere near that kind of heat and radiation. You don't just need a better air conditioner, you need entirely new materials and active protection systems that can handle a prolonged stare into the Sun. So right now, Parker's trajectory is a one-way, robot-only club. It's great for a hardened probe with no people on board, but completely off the table for a crewed Pluto mission. That pushes you to a tough question. What would it take to build a Parker-class ship that humans could ride? And would that actually change your Pluto answer in a meaningful way? Think about the kind of engineering leap that would require. You'd need heat shields that can shrug off thousands of degrees without eroding. You'd need active cooling systems that can constantly move heat away from the crew habitat. You would probably need some form of magnetic or plasma shielding to protect against charged particles coming off the Sun at close range. You might separate the reactor and engine sections on long booms, or use spinning structures to keep people far from the worst radiation. If you somehow solved all of that, then, in theory, you could run a similar play to Parker, dive close to the Sun, let gravity crank your speed up into the hundreds of thousands of miles per hour, then rotate your trajectory outbound and blast away toward Pluto. You would still need some kind of advanced propulsion to brake at the far end, but now your starting point is much better. Under that kind of architecture, your honest answer to how long to Pluto could drop into the 1 to 3 year window, depending on how aggressive you were with the dive and how powerful your outbound and braking engines were. That sounds almost too good, so here's the reality check you cannot skip. Physics does not forbid this. Nothing in Einstein's relativity says you can't go 430,000 miles per hour with humans on board. At that speed, you're still well under 0.1% of light speed. Time dilation is tiny. Relativistic effects are not your main problem. The barrier is not the speed of light, the barrier is engineering. Right now, Parker Solar Probe is a proof of concept for velocity, not for human travel. It proves that with the right trajectory and enough flybys, a spacecraft can hit nearly 500,000 miles per hour. It does not prove that you can strap a pressurized human habitat, radiation shielding, life support, and all the structure and redundancy you need onto that same profile and survive the heat and radiation near the Sun. We are many major technology steps away from being able to pull that off, so you're stuck in a strange place. You know we can technically reach speeds that would turn the Pluto timeline from decades into about a year. You know, physics will happily allow you to go even faster if your engines and materials can handle it. But you also know that with the hardware we have, those speeds only show up in extremely hostile zones that are completely off limits to human crews. That raises the next logical question. If we've already proven that insane speeds are possible, what happens if you keep pushing past Parker? Not just in clever trajectories, but in pure velocity, right up toward a serious fraction of light speed? Does Pluto start looking like a quick detour on the way to somewhere else? Or do you find out that for distances this small, even near relativistic travel doesn't really change the basic story of how hard it is to get there? Light sets the real upper limit on this whole conversation, so let's put numbers on it. From Earth's orbit out to Pluto's average orbital distance, light needs around 5 to 6 hours. That's it. A signal leaves near Earth's distance from the Sun, and half a workday later it crosses Pluto's orbit. If you had a ship that could cruise at even a tenth of that speed, around 67 million miles per hour, you would turn the entire trip into something that takes a few days instead of 10 years. Compared to everything we've talked about so far, that sounds like straight up magic. So the obvious question is, do we have any engine concepts that even point in that direction? On paper, yes. There are speculative designs that push exhaust speeds up to a serious fraction of light speed. Antimatter catalyzed fusion, for example, where tiny amounts of antimatter trigger fusion reactions in normal fuel. Or pure fusion drives with extreme confinement. Or Bussard ramjets that scoop interstellar hydrogen with huge magnetic fields and burn it as you go. There are also ideas for beam-driven craft, where giant lasers or microwave arrays back home push a light sail so the ship doesn't need to carry most of its propellant. In idealized studies, these systems can reach speeds where Pluto really does become a long weekend trip. You accelerate for a short time, cruise near a big fraction of light speed, then flip and brake, and the whole thing wraps up in days, not years. But then you look at what they require in practice and the entire picture collapses. We don't have industrial-scale antimatter production. The amounts we can make now are tiny and absurdly expensive, nowhere near what you'd need for a drive. We don't have fusion reactors that can run as compact, reliable rocket engines, let alone ones that throw exhaust out at a decent fraction of light speed. And interstellar fuel scoops like Bussard ramjets run into real physical problems, like drag from the scoop field and low particle density in real space. Warp drives take the speculation even further. Concepts like the Alcubierre warp metric don't try to accelerate a ship through space faster than light. Instead, they bend space-time itself, compressing it in front of the ship and expanding it behind. In the math, the ship can ride inside a bubble that moves faster than light relative to distant observers, without the ship itself locally breaking the light speed limit. It's a clever way to sneak around relativity's usual rules. But when you plug real physics into that metric, the problems jump out. To create and sustain that warp bubble, the equations demand exotic forms of negative energy density. The kind of stuff that, as far as we know, doesn't exist in usable amounts. You're talking about energy requirements that rival entire stars, organized into precise stable configurations. That is way beyond what even our most optimistic particle accelerators or quantum technologies can do. So right now, warp drives live in the domain of theoretical exercises and science fiction, not actionable mission design. You might think, okay, fine, no warp, but what about just going really fast in a normal way? Doesn't relativity at least help a bit if you get close to light speed? Relativity does something interesting here, but not in the way that helps a Pluto mission today. At very high speeds, like 90% of the speed of light, time dilation starts to matter. The clocks on the ship tick slower compared to clocks back on Earth. For the crew, less time passes than for people staying home. For interstellar trips over many light years, that can be a big deal. A journey that takes decades from Earth's viewpoint might feel shorter for the travellers. For Pluto, the distances are simply too small. Even if you could somehow get a ship up to 90% of light speed, the raw light travel time is still just hours. The difference between how much time passes on Earth and how much passes on the ship would be tiny in human terms. And long before you got to worry about that, you would have slammed headfirst into all the engineering problems we've already hit at much lower speeds, like shielding against radiation, handling waste heat, and generating the insane amounts of energy needed to accelerate and decelerate a crewed vehicle to those speeds without vaporizing it. So for Pluto specifically, relativity is almost a distraction. The distances are big enough to make our current rockets look pathetic, but small enough that relativistic tricks don't save you from the main problems. You don't lose the battle because Einstein's equations say no, you lose it because you can't build engines, power systems, structures, and shields that can handle the performance those equations allow. That's the key takeaway. When you answer, how long would it really take us to go to Pluto? Relativity, warp drives, and antimatter rockets are good for context. They tell you that physics, in principle, does not forbid fast trips. There's no law saying Pluto can't be a few days away destination if you somehow had near light speed capability. The hard limit is just the speed of light, not some hidden barrier much lower than that. But there is a huge gap between physics allows it and we can build it. Right now, that gap is measured in many decades of research, infrastructure, and technological leaps. None of these relativistic ideas change the concrete reality that, with anything remotely like our current or near-future toolkit, Pluto remains a mission you measure in many years, and for humans, probably in decades. And that leads to a very different kind of question, one that has nothing to do with exotic drives and everything to do with people. If the physics and the engineering together keep dragging your Pluto timeline into the 10, 15, or 20-year range, what does that actually do to the humans on board? What does it mean to turn a big chunk of your life into one long, fragile line through deep space? When you stretch a Pluto mission out to realistic numbers with current or near-future tech, you're not talking about a trip, you're talking about a big slice of a human life. A chemically or modestly nuclear-powered mission, with real training, outbound crews, time in the Pluto system, and a way home, very easily lands in the 15 to 30-year range, end to end. That means someone might start training in their 20s, launch in their 30s, and come back to Earth in their 40s or 50s or later. At that point, your how long question stops being just about engines and orbits. Crew psychology, social structure, and mental health become as critical as propulsion and life support. So you face a hard design decision. Do you keep missions inside a single person's working life, or do you start thinking about generational crews? The first model says, you leave as an adult, you return before you're elderly. Launch in your early 30s, come back in your 50s. That is already a huge commitment. You sacrifice normal career paths, normal family life on Earth, and you spend a massive chunk of your prime years inside a metal habitat. The alternative is even more extreme. You accept that some crew members might be born on the way, grow up in space, and maybe never see Earth until they're adults, if at all. For Pluto-scale distances with engines you can actually imagine building in the next few decades, we're still in the one career, one mission zone. You can just about fit training, outbound leg, operations, and return inside a long but finite working life. But the numbers push right up against that boundary. Stretch the trip just a bit, slower propulsion, extra time loitering in the Pluto system, more conservative trajectories, and you start to cross into a regime where born on the ship is no longer just sci-fi flavour, it's part of the mission architecture. On top of that, you're carrying a constant invisible threat, radiation. In low Earth orbit, like on the ISS, crews see more radiation than on the ground, but they're protected by a big chunk of Earth's magnetic field and atmosphere, and they're only up there for months. On a 10 to 20-year deep space mission, you're outside that shield almost the entire time. Even if the background cosmic ray level is modest by space standards, thousands of days of exposure add up. To keep lifetime cancer risks and other radiation damage within limits we're willing to accept, you need serious shielding. That might be thick layers of water, polyethylene, or specialized materials wrapped around crew quarters. It can be clever use of fuel, water tanks, and cargo as a makeshift shield. You might even look at active shielding concepts using magnetic or electric fields. But every extra pound of shielding you add increases the mass of the ship. More mass means more fuel to accelerate and decelerate. More fuel means bigger engines, more launches, more cost. And if more mass makes the trip slower, your time in the radiation environment grows, which pushes you to add even more shielding. You're always trying to land on a sweet spot where mission duration and protection add up to a total dose that is high, but not catastrophic. Then there's the communications problem that hits you once you're actually at Pluto. Radio waves still move at the speed of light, but the distance is brutal. Depending on where Earth and Pluto are in their orbits, a one-way signal takes roughly 4 to 7 hours. That means there is no such thing as a real-time conversation with mission control. You cannot say, "Houston, we have a problem," and expect an answer in the next few minutes. Every exchange is delayed. You send a question, and you wait most of the day for a response to even reach you. Then they wait for your reply. That delay forces a completely different mission philosophy. The crew has to be highly autonomous. They need the authority and training to make major decisions on their own, often without waiting for Earth. Mission control becomes more like a consultation service than a direct controller. Procedures have to be written with the idea that if something breaks badly, the people on the ship are the primary responders, not the people on the ground. That changes how you train, how you pick personalities, and how you set up the command structure on board. Psychology becomes the quiet backbone of the whole operation. Long-duration isolation already shows up on the ISS and in Antarctic stations, and those are small-time samples compared to a Pluto mission. You're looking at years in a closed environment with the same small group of people, no possibility of going outside without a suit, and no quick way home if someone has a crisis. You have to plan for conflict management, boredom, depression, and the simple fact that people change over decades. A crew that works perfectly together in year 1 might feel very different by year 10. This loops right back into your core question about time. The longer the mission, the harder every human factor problem hits you. Radiation dose rises, life support systems have more time to fail. Psychological stress piles up, social dynamics get more complex. Skills need to be refreshed and upgraded mid-mission. You can mitigate some of it with better training, better ship design, and better support from Earth, but you cannot erase the basic connection. Time in deep space multiplies risk for people. That's why engineers and mission planners keep coming back to one quiet target: get the transit time under a decade if you can. If you can leave Earth and reach Pluto in say 6 to 8 years instead of 15, a lot of the worst case human issues stay in a range we at least understand from current experience and analogues. Life support still has to be robust, but it's not being asked to run flawlessly for 30 years. Radiation shielding still has to be heavy, but total dose is less. Crew social structures are still stressed, but not stretched across a whole working lifetime. Let those numbers drift upward, and the mission stops looking like an extreme expedition and starts looking like a fragile tiny society drifting through the Kuiper Belt. At that point, your problems are no longer just propulsion and structure. They're sociology, medicine, and long-term psychology, all playing out in a place where one major failure can kill everyone on board. And this is where another layer of reality hits. Even if you solve the engineering and human problems on paper, you still have to deal with budgets, launch infrastructure, and risk tolerance back on Earth. So the next question is not just can we go, or can we survive the trip? It becomes, will anyone actually pay for this, build it, and accept the risks over the decades it would take to make a human Pluto mission real at all? Up to now, we've treated the Pluto mission like a pure engineering puzzle, as if you could just pick an engine, pick a timeline, and go. In the real world, the answer to how long would it take is welded to a much uglier variable: how much money you're actually willing to throw at the problem, and how much risk you're willing to tolerate along the way. Start with budget. Apollo's the clearest example we have of what happens when a country decides, we are going to do this fast no matter what it costs. Massive funding, concentrated will, and national prestige all aimed at one goal took a moon landing from concept to reality in less than a decade. If you did something similar for Pluto, if you said, we are going to own the outer solar system, and back that up with hundreds of billions of dollars over decades, nuclear propulsion and megawatt-class power systems would appear much faster. You'd see big test reactors, big electric propulsion stacks, and dedicated deep space habitats pushed through design and into hardware on aggressive timelines. If you don't do that, if Pluto is just one line item among many, your answer to how long automatically includes decades of development before you ever roll anything onto a launch pad. Nuclear thermal propulsion creeps along on limited budgets. Nuclear electric systems move from study to small demo. Life support research advances, but slowly. In that world, your Pluto timeline is not just 10 years of flight. It's 10, 20, or more years of getting the technology to the point where you'd even trust it with an uncrewed mission, let alone a human crew. Then there's the safety ladder for new engines. Before you put people on top of a brand new nuclear rocket or a high-power electric propulsion system, you absolutely have to test it, more than once, in space without anyone on board. That means a sequence of robotic demos. First, maybe a small tech demonstrator just to prove the reactor and propulsion system can run in orbit. Then a bigger craft that actually does a serious deep space mission, maybe a fast Jupiter or Saturn trip, maybe a Pluto orbiter with no crew. Each step takes years of design, construction, launch, and operations. If you're serious about fast Pluto, you're not just choosing one stack of technology, you're layering them. Nuclear thermal engines, nuclear electric propulsion, advanced life support, high-mass shielding, new navigation and autonomy systems. Each one has its own testing ladder, its own decade-scale path from lab to flight-proven. Add those together, and you quickly see how the calendar balloons. Even if the final crewed Pluto ship could reach the dwarf planet in 8 years, you might spend 20 getting those systems ready and proven. Now look at launch infrastructure. A serious human Pluto expedition is not something you send up on one rocket. You're likely talking about multiple heavy lift launches, maybe dozens to put all the pieces into orbit. Habitats, propulsion stages, reactors, shielding, propellant tanks, cargo, return stages. You could assemble the ship in low Earth orbit, but it might be safer or more efficient to build it at a staging point, like a high Earth orbit, a lunar orbit, or a Lagrange point where gravitational forces balance out. To support that, you probably need fuel depots in space, places where tugs can top off tanks, places where you can store propellant over years. You may want a lunar base or industrial infrastructure on the moon to supply some of that propellant or shielding material. None of that exists at scale today. Building it is itself a multi-year to decade-scale program. So the honest version of your answer is not just X years from launch to Pluto, it's plus around 10 or more years to build the gas stations and assembly yards before you even start the clock on the main mission. On top of everything, risk appetite is a quiet but massive lever on the schedule. In the Apollo era, leaders accepted risk levels that would be shocking for a commercial airline. Several % chance of crew loss over a program was not considered insane. That attitude lets you move faster. You test less, you accept more uncertainty, and you fly more aggressive trajectories because you're willing to roll the dice. If you demand airline-level safety for a Pluto mission, tiny probabilities of catastrophic failure, well, your process changes completely. You add redundancy everywhere. You test every major system in flight-like conditions multiple times. You insist on incremental stepping stones, from cislunar missions to Mars missions to deep space shakedowns before you ever commit to a Pluto shot. Each one of those steps adds 5, 8, 10 years to the overall pathway. The more safety you demand, the more the calendar stretches. This is where the question itself starts to shift. Very quickly, how long would it take to go to Pluto turns into, how long would it take for us to even decide to do Pluto for real? Even with the tech we have today, a repeat of New Horizons, a robotic flyby, is something we know how to do in roughly a decade, from funded start to arrival, if someone writes the checks. You design a new probe, pick a launch vehicle, look for a Jupiter assist, and fly a familiar profile. The physics and engineering are understood. You're mostly fighting budget cycles and launch windows. A crewed landing or even a crewed orbital mission is a different animal. That program would likely spend years, maybe a full decade, just in studies and trade-offs. Committees arguing over propulsion choices, space agencies debating nuclear reactors in orbit, teams running simulations of radiation doses, mission profiles, abort options. You'd see roadmaps drawn up, revised, and thrown out before any real hardware is cut. That's not wasted time. You have to get the design right, but it means your Pluto timeline is not just flight time plus training, it's design plus testing plus infrastructure plus flight. So when you keep pressing on this simple question, how long would it really take us to go to Pluto? You eventually reach a layered answer. There's the clean physics answer, based on distances and speeds. There's the engineering answer, based on engines, shielding, and life support. Then there's the real-world answer, based on budgets, risk tolerance, and how fast society is willing to move. And that sets you up for the final step in this whole chain. If we actually started now and today, and pushed hard, what does a realistic path to human standing on Pluto's surface look like in total years? From the moment the program is greenlit to the moment boots touch nitrogen ice. If you really start the clock today and ask, when do humans actually stand on Pluto and come back alive? You can't just look at engines or orbits. You have to line up a whole stack of technologies that all need to mature together. And right now, every major one is either experimental on paper or only proven for much shorter, easier missions. For a start, you need a propulsion system that's better than chemical rockets. That means reliable nuclear thermal or nuclear electric propulsion, not just in a lab but in space running for years. You need a deep space habitat that can operate for decades, not months, and still support human health. You need serious radiation protection, either high mass shielding wrapped around your living areas or some kind of active protection like magnetic or plasma shields that can take the edge off cosmic rays and solar storms. And on top of that, you need autonomous systems that can handle 4 to 7 hour communication delays with Earth, because the crew won't be able to ask mission control about every serious decision and get a useful answer in time. Right now, every item on that list is at best early stage. We've played with nuclear thermal concepts on the ground. We've done small-scale nuclear electric and radioisotope systems for less power, not propulsion. Our space habitats have proven they can last years, but not flawlessly for decades in deep space. Radiation shielding is still a nasty mass trade, and autonomy while advancing fast has not yet been tested in a crewed far-out mission with huge communication delays and no quick rescue. None of these are fully flight qualified for missions that run 20 years end to end. So the first chunk of your timeline isn't flight, it's development. If we got serious right now, real money, real priority, you might see flight-ready nuclear propulsion in about 10 to 20 years. That path would include building reactors, testing them extensively on the ground, doing subscale demos in orbit, and then flying one or more uncrewed deep space missions to prove they work outside Earth's neighbourhood. Only after those systems are proven would anyone sign off on bolting a habitat to them and sending people. And remember, propulsion isn't the only long pole. Deep space habitats need their own test missions, maybe in cislunar space, maybe on long Mars-class flights. Radiation protection strategies need to be validated with actual dose measurements over multi-year stretches. Autonomy software needs to be shaken out in situations where it's allowed to make high-level decisions with real consequences. All of that eats time, so before you see a Pluto crew climbing a ladder into their ship, you've probably already burned 10 to 20 years on technology maturation and demo flights. Once you finally have the tools, you can talk about the mission itself. With nuclear propulsion, a reasonable first-cut design might get you from Earth to Pluto in something like 5 to 8 years, one way. That assumes you're using either nuclear thermal or nuclear electric setups, or some hybrid to accelerate harder and longer than a chemical system, while still keeping propellant needs under control. You then spend maybe a year in the Pluto system itself, entering orbit, mapping, landing, surface operations, sample collection and system checks. Then you still have to come home. Unless you want a one-way mission, which is not ethically acceptable for a first Pluto attempt, you need another 5 to 8 years for the return leg. Add it up and you're looking at a round trip somewhere in the 11 to 17 year range. Push hard and accept more risk. Maybe you push toward the low end. Go conservative with more margins, slower profiles and extra loiter time, and you drift toward the high end or beyond. And that's just from launch to touchdown back on Earth. When you stack everything together, development, testing, infrastructure build-out and the mission itself, your total human Pluto program runs on the scale of 2 to 4 decades. If you kick off serious funding in year 0, you probably don't see a crew actually walking on Pluto's nitrogen ice for at least 20 years, and it could easily be closer to 30 or 40 depending on setbacks and how cautious the world decides to be. That's the real answer hiding behind the numbers. A funded, focused human Pluto program is not a 5-year sprint. It's a generational project. The engineer who signs off on the propulsion architecture might be in high school when the first big development contracts are awarded. The mission commander who steps onto Pluto's surface might be in elementary school when the initial design reviews are happening. By the time they fly, an entire cohort of scientists and engineers will have spent their main careers building, testing, and tuning the systems that make that landing possible. From the crew's perspective, you're asking them to commit a huge slice of their lifetime to one mission. They might join the program in their 20s, train through their 30s, launch in their late 30s or early 40s, spend a decade plus in flight, and come home in their 50s or 60s. For them, Pluto isn't an assignment, it's the central story of their adult life. For ground teams, it's the same. People who design early components may retire before the mission comes back. So when you ask, how long would it really take us to go to Pluto? The answer in the human case is not just 10 to 15 years in space. It's 20 to 40 years from the moment we commit to the moment boots touch down and samples return. You're measuring in miles and miles per hour, yes, but also in careers, job markets, and whole human generations. And after you've followed all of this, the distances, the speeds, the engines, the human factors, the budgets, you're finally ready for the short version. The one line you can actually say out loud on camera that wraps the whole story into something people can feel without lying about the physics. So after everything you've heard, you still want the number. How long does it really take to go to Pluto? Not in fantasy mode, but with real hardware and real physics. Let's strip it down. Right now, with off-the-shelf tech, the cleanest answer we actually trust is the New Horizons playbook. If you launched a similar probe tomorrow, same kind of mass, same kind of chemical upper stages, same kind of Jupiter assist, you'd be looking at something like 9 to 12 years for another flyby. The big swing factor is not the engine, it's geometry. Where Earth and Pluto are in their orbits when you leave, whether Jupiter is in a good spot for a slingshot, how much extra speed you can squeeze out of that gravity assist. In a good alignment, you end up near the low end, around 9 or 10 years. In a worse one, you creep toward 11 or 12. That's the uncrewed, we know how to do this regime. Now pivot to humans, but don't change the tech. No nuclear engines, no new propulsion, just big chemical rockets, something like SLS class lift, and life support stretched way beyond ISS durations. You don't want to flyby, you want to actually arrive and stop at Pluto, probably enter orbit, maybe land. With the rockets we actually have, that pushes you into a very ugly corner. To accelerate a heavy shielded crewed ship to Pluto-class speeds, then carry enough propellant to brake at the far end, you're talking about huge propellant mass, many heavy launch years, and timelines that almost certainly run past 20 years total. Mission start to mission end, even if everything works. It isn't forbidden by physics, but with current infrastructure, it's not remotely practical. It would eat an entire generation of launch capacity and budget just to put one crew in the outer dark. So the natural question is, what happens if you add the technologies we've been circling around, nuclear thermal and nuclear electric propulsion, plus advanced electric thrusters? If those are mature, your numbers shift in a way that actually matters. A robotic orbiter, not a flyby, could probably reach Pluto in around 5 to 8 years, depending on how aggressive your trajectory is. You accelerate harder and longer, you keep pushing on the way out, and you keep enough delta in reserve to slow down and stay. For humans, after you've done the test flights and shaken out the bugs, you'd aim for something similar, maybe 5 to 8 years each way, with around a year operating in the Pluto system. That gives you an 11 to 17 year round trip from launch to landing back on Earth for the crew. But remember, That sits on top of 10 to 20 years of tech development and demo missions before you ever fly the first person. So from the moment someone signs the budget line to the moment a human actually kicks nitrogen ice on Sputnik Planitia, you're looking at a total program span on the order of 20 to 30 years if things go well, and longer if they don't. All of that is still far slower than what physics would allow in the best case. If you use Parker solar probe class speeds as a sanity check, a few 100,000 miles per hour, and you pretend you can safely accelerate and brake a crewed ship at that level, the lower bound for a sensible headline travel time to Pluto lands around 1 year, give or take. Maybe a bit less in a very tight profile, maybe a bit more if you're conservative. That's still well under the 5 to 10 year numbers we keep quoting. It proves something important. The universe is not stopping you from making Pluto a months-long or 1 year trip. The roadblock is not the speed of light, it's your ability to build engines, reactors, structures and shields that can do that without killing everyone on board. So you end up with a layered, honest answer. Right now, with the rockets and hardware actually on the shelf, Pluto is roughly a decade away for a small robot that never slows down, and effectively more than 20 years of total mission time for a crew that wants to arrive and stop. If you somehow brute force it with chemistry alone. With near-future nuclear and electric propulsion that we can plausibly develop, you can talk about robotic orbiters in 5 to 8 years of flight time, and human expeditions with 5 to 8 years each way, inside a larger 20 to 30 year program window. And if you look at the raw physics limit, using record speeds like Parker's as a benchmark, you see that in principle Pluto could be pulled down into the 1 year travel time regime, but only if your engineering jumps forward by an entire era. That's why when you want one line that hits hard and still respects the numbers, the answer sounds like this. With the rockets we actually have, Pluto is at least a decade away for a robot, and probably a couple of decades away for a human crew, but the moment we master nuclear engines or Parker-class speeds, that 3 to 5 billion mile gulf collapses from a lifetime to something you could cross in a single terrifying unforgettable year. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.